Hello, this video is on work, using calculus to evaluate work. Now, I'm only limiting this discussion to Hooke's laws of springs. I'm sorry if you needed it for other content, such as gravitational forces and things like that, but I'm only covering this particular type of example in this video, which relates to what I teach in my class and test over. All right, so suppose, the basic idea in physics, if you have a constant force, work would equal force times distance. However, what if the force was variable, meaning, it took a different level of force to move something a different distance? Let's see. Now, if an object's moved along a straight line by a continuously varying force, the work done by the force as you move it from A to B would be the definite integral from A to B of f of x dx, where f of x is the kx, where k is what's called the constant of proportionality. So, in other words, suppose if you're moving something a certain distance and maybe the first meter, it takes a certain force, and maybe it takes a certain proportion of that force to move it the next meter for whatever reasons. I'm not worried about that, and then that same proportion to move it another meter, that's where you would have a variable force, meaning it's not constant. It's depending on how far you're moving it and what particular point you're moving it to. So here, as I mentioned, Hooke's law of springs. And let's take a look at this. We're going to look at stretching and compressing a spring, which essentially has the same effect. So you kind of treat it the same way, whether it's stretching or compressing. So here's a picture of a spring. You look at this and go, and you can imagine with a spring, of course, that's obviously a big, thick, heavy spring, but if it was one that you could move yourself, you push it in, and then as it gets pushed in, it'll get harder to push in, each subsequent distance. So it would have a variable force. This really isn't too bad because every integral here is going to be simple, because all of it, you're just going to be integrating something with x in it. That's it. So once you get this set up properly, there are a couple of tricky situations we'll see here, but you get it set up properly, the evaluation is really easy. All right, so suppose it takes 2,500 newtons to stretch a spring 5 meters from its resting position. So we have a force, which is 2,500, and we have a distance, which is 5, meaning that we have to solve for this constant of proportionality k. And that's really easy. So you just come over here and say 2,500 equals k times 5. Therefore, k equals 500. And that means our force function will be 500x. So wherever we're going to integrate this across what path, distance-wise, we'll be integrating 500x. So this first part A here says how much work is done by stretching the spring 5 meters from its resting position. All right. So 500x dx, resting position means it's at 0. You have not moved it at all, whatever. So anytime you're at resting position, you're at 0, and you're stretching it out 5. So you're going from 0 to 5. Oops, don't want that. 500x dx. And there we go. So the antiderivative of x is 1/2 x squared. Put in 5, put in 0. Simple calculations. You can use, well, it depends on the instructor. If the instructor is me, but if it's another instructor, you could use the definite integral function in the calculator to get this. And that's actually 6,250 Newton meters, which in physics, 1 Newton meter is a joule. Called a joule. That's all right. I mean, that's very important. I don't know how, I'm not picky about that. I'm not sure how other math professors would feel. But I can promise you a physics professor would want those units to be right, physics or engineering. But on my handwritten exams, I usually don't require them to have to put the units there, or if they did put a unit there and got it wrong. But I think for your overall educational experience, with if you're in any kind of sciences, physics, engineering, yeah, I'd start learning how to get the units right. And usually students taking physics will confirm that, when I'm teaching a face-to-face class, they'll say, yeah, that's important. So, all right. And I remember it being important, 100 years ago when I took classes like that. But it's nice to get an opinion from, modern day students who also verify that was important. So, all right, the next one says how much work is done in stretching the spring from 2 meters to 7 meters. So that means we're starting at, as far as measurement purposes, obviously you have to stretch it to get to 2, but we're only measuring it from the point where it's 2 to the point where it's 7. So 2 to 7, same force function, 500x dx. So that's 1/2 x squared, so it makes the 500 become 250, just like up here. Actually, up there I actually wrote 500 times 1/2. I did not down here. And put in 7, put in 2, and this time we have a 11,250 joules required to go from 2 to 7. I just thought I'd mention this. You see, it's taking a little more work. See, even though it still went only a distance of 5, 0 to 5 and 2 to 7 are both distances of 5, the variable force means it's getting harder to move it, to stretch it. So that's why it took more work, even though it was the same distance. It's because it was at a different point where the spring was being stretched. So they wasn't going to be consistently just. That's where it just goes back to simple physics. If you were didn't have a variable force times distance, it would be the same. From 0 to 5 and 2 to 7 would be the exact same work, but not in a variable force. All right, so this time what I do, I use newtons, but I use centimeters this time instead of meters, which converting centimeters to meters is not difficult. If you need to, all you have to do is divide by 100. So this says how much work is done by compressing the spring 2 centimeters from its natural position. So it doesn't matter in this case how long the spring is. Well, obviously it's more than 2. I'm sorry, it does give the length. We do have to know the length. Excuse me. The last one we didn't have to know the length. This one we know it's 15 centimeters total. So pushing it in 2 from its original position. And so 5 newtons moved at 3 centimeters. So we can solve for the k here. So 5 equals 3k, 5/3. So the force function will be 5/3 x using centimeters. Which, like I said, we can convert this to meters to be for joules purposes, if that's required. So the function is 5/3 x dx, 0 to 2. So it's 5/3 times 1/2 x squared, 0 to 2, put in 2, put in 0, that's 5 over 6. Well, technically it's 10/3 Newton centimeters if you want to use Newton centimeters. Like if you were using English units, a lot of times you'd see foot pounds. But since Newton centimeters can be easily converted to another measurement, joules, all you have to do is divide by 100. So 10 over 3 times 1 over 100 equals 1/30th of a joule. Now this next one, part B, is tricky, and I always like to put this on my exam because frankly it's about the only thing that makes the spring problems challenging, or you at least have to think a little bit. How much work is done compressing the spring from a length of 10 centimeters to a final length of 6? The common mistake on this is to automatically assume the limits of integration are going to be 6 and they're going to be 10. But that's not the case. Let's go back and look at the length of the spring. It's 15 centimeters. If the spring is at a length of 10 centimeters when you're first starting the measurement, it's at a length of 10 centimeters, that means it's been pressed in 5 centimeters, like I have right down there. It's been pressed in 5 centimeters. And then as it's pressed and you're stopping your measurement where the spring has a length of 6 centimeters, if it's 15 centimeters long and you're measuring it at 6 centimeters, that means you've compressed it 9 centimeters. So the limits of integration would not be 6 to 10, they would actually be 5 to 9. So you see my picture down here means it's gone in 5 centimeters to be 10 long, and then here it's gone in 9 centimeters to leave you 6 there. So the red represents the lengths after it's been compressed, and then the purple shows you how far it had to be compressed. So this problem was important that we knew the total length of the spring. We had to know that. So another way to look at it, it's just the 6 and the 10. Just take, you take the total length minus one of those numbers, total length minus the other, and of course the smaller number when you evaluate it has to be on bottom. So 15 minus 10 is 5, and then 15 minus 6 is 9. So it's going to go from 5 to 9. So sometimes that kind of throws people off, and I guess they get used to it eventually as long as they study and prepare properly. But so it's not those numbers that are given in the problem, it's the total length of the spring minus those numbers. Alright, so after all that's settled, then it's easy. So the antiderivative of 5/3 x is 5/3 times 1/2 x squared, so it's 5/6 x squared. Put in 81, put in 25. I don't know, it just depends on whether your instructor is would have you use what's called an exact answer, meaning like a fraction or square root or decimal, but I just did it as an exact answer. So it's 140 over 3 Newton centimeters, and then multiplying it by 1 over 100 again to convert it to joules would make 14 over 30, which I then reduced to 7 over 15, which, I'm not big on if somebody doesn't reduce it, but you may be in a situation where that's important. I'd have been perfectly happy with 14 over 30 joules. All right, so this one's a little bit different. So instead of giving us the the force amount and the distance amount to solve for K, they're actually giving us a work amount and enough information where we can solve for K that way. So it's just a different way to solve for K, and then we'll apply it to a work in the next statement. So this says 80 joules of work requires to stretch a spring 4 meters from its natural length, meaning natural length starting 0. So this time we know the work answer. The work answer will be 80. And from 0 to 4, we don't know K, and of course that's always x dx right there. So what we're trying to do is then integrate this, then algebraically solve for K. So once you kind of see how it's set up, it's not hard to solve. But see, so the work is already known here. So then, of course, you have 1/2 x squared. I left the 80 over here, so 1/2. I guess. Oh well, I can just explain it. I didn't write it out. But 4 squared is 16 minus 0 squared, so it makes it 16. 1/2 of 16 makes that 8. So that's where the 8K is coming from. So K equals 10. So that's just a different way to how to come up with that value for K. Force equals 10x, and that's our force function. Now let's see what the second question says. Find the work required to stretch the spring an additional 3 meters from the original 4 meters. All right. So we're starting at that 4. So you're saying it's additional 3 from the 4. So that means you're starting at 4. 3 more will take you to 7. So basically you're going from 4 to 7, which would be an additional 3 meters. Okie doke. And so there we have it. 10x dx. Antiderivative of that would be 5x squared. Put in 7, put in 4. 5 times 49 minus 16. is 165 Newton meters. So since we're not using centimeters this time, we are already in the joules format. And when I put these flags, I'm kind of indicating, that is the right answer. Technically, it's the right answer. All I've done here is just change the units to joules. Okay, so that concludes this video on work with Hooke's law for springs. So, the end.